Hello, I'm audible.
Yes, you are, Jameer. Go ahead.
Hi, Prakash. Is
Hi.
Desh is also here?
Yes,
Yeah.
I can see him in the list.
Hi, Desh. Okay.
Hi.
Hope my screen is visible.
Yes, it is.
Okay. Shall we start or shall we wait for another 2 minutes?
Up to you.
We'll wait for a minute and then let's start.
Sure.
Let's start, I guess. So, hello everyone. So today we will discuss about some radio experiment, the first radio experiment. There are two radio experiments. So we'll discuss about first experiments today and the second experiment in upcoming weeks. Okay, so I'm myself Jameer. So along with me, Avinash Deshpande, Desh is here. Prakash is also here with us. Okay, we all are working here in IUCAA. So we designed this experiment in such a way that one can perform this experiment using the available resources at home. Okay, so these are some analogy what we used in our like daily day. Just yeah. So daily life. So we'll perform this experiment and we can learn a lot of things like for example, so how the electromagnetic wave fall by 1 by r square, okay, how the intensity is 1 by 1 by r square, okay. And what if we place a reflector, okay, there are different type of reflectors. For example, there's a plane reflector, there's a parabolic reflector, okay. There is a spherical reflector, corner reflector. Those are act as an antennas. And what is the effect when we place this behind or in front? We are going to see, and based on that, we have designed such experiments. So there are 4 to 5 experiments which you can refer in our like Moodle platform as well as in IUCAA repository. Okay, in like TLC, we have designed few experiments, so you can refer there. So we'll see the first experiment here, okay, so which is the effect of putting a reflector at the back of the antenna, okay. So if you take any antenna, whether it's a simple antenna, dipole antenna, any type of antenna, so once you put a reflector at the back of it, and we'll see what are the effect and where exactly we need to put the like to get a better perform, okay. So we'll see those things here. So this is our first experiment, and as I was explaining, so the intensity dropped by like 1 by r square. So if there's a total intensity I0 here, so it drop by like 1 by suppose if it's a unit area, it will drop by 1 by 4 pi r square. Okay, so that we know, and we'll see what happens when we put the antenna. Here we are using a plain reflector antenna. So either you can take any metal sheet. So if you don't have metal sheet, it's okay. So what we can do, we can take a aluminum foil and we can take a cardboard and we can paste it. So it will act as an like plain reflector or an antenna. Okay. So you can use that, and you need a transmitter, okay, or an antenna. So which we can use either a cell phone, or you can use your router. Okay, because our cell phones also, they also have the antenna. Okay, so these are Wi-Fi antennas. What we are using is here Wi-Fi. Okay, so we can use those antenna, but we are not showing Wi-Fi antennas here for the simplicity. So suppose these are the two dipole antenna, and we have placed a plain back reflector here. Okay, and the propagation of the waves are in this direction, in the direction of Z. Okay. So we see the change in the intensity here based on the distance between the antenna and the plane reflector. Okay, we also see an image of the antenna like in optics we see. So whenever those are in phase, like we might have like gone through the constructive and destructive interference. So whenever there is a constructive interference, we get the maximum intensity here. So likewise, at a when we place this antenna at a proper distance, okay, the back reflector with respect to the antenna, we get the maximum intensity or the power at the receiver side. So this is also called as an array factor of antenna. So here there's another illustrative here. So this is your cell phone. Suppose this is the transmitter you're using as a cell phone, and this is the plane reflector we are keeping here. So it will emit the waves in all direction. So and the waves which are directly reflecting from the reflector, when it comes in a phase, then the power will get added up at the receiver side, and we see the maximum power received at the receiver side. At the receiver side, either you can use cell phone or laptop or any device which you can like connect to the Wi-Fi connector here to the transmitter. So this is a simple experiment what we can perform at home. Okay, so what you need here, like hardware wise, we are mentioning here, you need a transmitter side. So either a smartphone or a router, Wi-Fi router. So you can use anything. Even if you want to use laptop, that's okay. But we like recommend you to use cell phone or Wi-Fi router in the absence of like smartphones. Okay, it can be act as a transmitter. So once you have the transmitter at the receiver side, what you need, either you need a laptop, or you can connect, you can take another cell phone, so which will act as a receiver. So you need to connect to that Wi-Fi like a router or a transmitter. So you can measure the power using some softwares. So we will come to the softwares, what softwares we recommend for different OS and all. So we'll come to that. So once you start receiving the like power on the receiver side, you can measure how much power you are receiving in dBm. Okay, and you need a measuring tape for distance measurement and a plane metal reflector. It can be any reflector. Okay, whether you can use aluminum sheet, you can use metal sheet, you can use copper sheet, or anything. So whichever you have. Like if you don't have any metal sheet, you can take aluminum foil. So it might be there in your home. So you can simply paste the aluminum foil on the cardboard, and it can be act as a simple reflector. For example, here we have two setups. Okay, here on the left side, what we have done here, we have pasted the aluminum foil on a cardboard, and with the help of this holder, we have kept the cell phone here. And in here, right side image, we have a copper sheet. Okay, so that will act as a back reflector antenna, and we have kept cell phone here. which need to be placed with the help of this box. We have like this will act as a support here. So what is the procedure here? So we need to like ensure your router is on, or you need to create an Wi-Fi hotspot on your cell phone or smartphone, and then you need to connect your both devices, which need transmitter to the receiver. Okay, and then disconnect the cell phones or mobile phones router from the internet. We need to make sure that these devices are not connected to the internet. If you're using a router, simply disconnect the LAN cable. If you're using a smartphone or cell phones, simply you disconnect the internet data, because of those packets, the internet packets and all, the power may fluctuate, okay, at the receiver side. So to avoid that, to avoid the errors, we are disconnecting this with the internet, as well as the like whether it's, if you're using router, we need to disconnect uh, the LAN cable, and if you're using smartphones, you simply either keep it on a plane mode, or you disconnect the internet data. uh, in some cell phones, it's not possible to create a hotspot when they are on a aeroplane mode. So in that case, you simply you can disable the aeroplane mode, and you can simply disconnect the internet data. Okay, and then take a metallic back reflector, okay, and place it at the back of the mobile, and we have to make sure it's perpendicular to the floor where we are placing this, and there should not be any slant, or they should not be kept at some angle. It should be exactly perpendicular to the plane where you're keeping this reflector, and your cell phones also need to be perpendicular to the floor. And then start moving your back reflector slowly, step by step. Okay, you can go at the step of like 0.5 centimeter or 1 centimeter. Okay, and then you slightly move it and wait for a few seconds, for at least a minute, around a minute. Okay, and then see whether the power is increasing or decreasing. So likewise, in those steps, say for 1 centimeter or zero point 0.5 centimeter, you can change slightly, because at the end of at the receiver end, the power may not reflect immediately. So it will take some time to settle down. So you have to wait for some time, and then you change it. And at that time, you will see whether the power is increasing or decreasing. And you have to also make sure that there is nothing in the direction or in the eyesight, the line of the sight between the transmitter and receiver. Even you can't come inside, otherwise those waves will be reflected back or scattered. Okay, you have to make sure there is nothing between the transmitter and the receiver side. And then you start increasing, and you see at what distance it is getting maxima and minima, or at least at what distance the power is maximum and the power is minimum. So you will start observing, and you can like start from the exactly very close to the back reflector, and you can go on increasing at the step of 0.5 centimeter, 0.5 centimeter, 1 centimeter. You can go up to few centimeter at least, and you will see the power is sometime increasing and decreasing likewise, and you can note it down. So the power, you can note it down in dBm, and distance you can note it down in the centimeter. And you, at the end, you can plot the the power or the signal strength versus the reflector distance, and you will get some output. And from that, you can infer. So you can get to know also at what wavelength it's operating. So if you're using Wi-Fi router or the cell phones, they operate at two frequencies. The first frequency is 2.4 gigahertz, and the second frequency is 5 gigahertz. We need to know at what frequency they are operating at. Okay, so if it is operating at 2.4 gigahertz, the wavelength is around like 12 centimeter, if I'm not wrong. Okay, so this is about 12 centimeter. So you will get to know at what wavelength so it is getting maxima, and what wavelength you're getting the minima. And there are few tips while performing this experiment. You need to find the physical location of an Wi-Fi antenna in your device, because that is very important. You need to know where the antenna is located in your device. If you are using router, so there are antennas, so easily you can find out. But when it comes to a cell phone or a laptop, a smartphone, so you need to see, and you can search online on the internet, so where these antenna are situated or located, okay, physically in your cell phones or receiver, because we also need to measure from there, and we need to make sure like the distance where it is kept, and the distance between the receiver and the transmitter, those also matters. So in other experiments, so similar things we need to keep. Okay, and keep your cell phones and laptop charged, because while performing, so it may take half an hour to 1 hour, so depend on how you're performing. So if the power goes off, so the they may you may also find some errors. Okay, and because due to temperature and other settings, so you may get some deflection from what you're expecting. Okay, so that's why once you start the experiment, you have to make sure the cell phone or laptops are charged, and the settings we should not change, and also we should not change the setup. We need to like take care of those things. And detecting might take a few seconds to settle down, as I already mentioned. So we need to give some time to settle down the readings. Okay, it's not suddenly changing as we change the distance or as we change the location of the antenna from the reflector. Okay, so we need to maintain that. And if the signal strength is going beyond 80 dBm, and we can stop there. So if you're getting like from say minus 30 dB to 80 dB, so those are fine. So if it is going beyond 80 to 90 dBm, so the signal strength will like the deflections are very minute, and you may not be able to detect those things. So you can stop there at that. So these are some tips you need to take care while performing this experiment. Okay, and yeah, we have to make sure that the data connection is simply off, and we don't need any data collection. It's always better to keep on aeroplane mode. So if you're not able to like keep on aeroplane mode while you're connecting with your Wi-Fi, so it's better to switch off the data connection. Okay, and remove these covers and all. So sometimes uh, in few covers there are metal coating on it, and it may affect your antenna. Okay, those are placed very close to the antenna, and that time may also affect your readings. So it's always better to remove the covers of a smartphone. Okay, and stand few meters like away from the setup, as I already mentioned you. So if you come nearby or in between, so due to reflection and the scattering, so your observation may get affected due to that. And once you start taking reading and observations, you have to make sure nobody is roaming around it, okay, near the setups. Otherwise uh, the receiver may pick up the reflected or the scattered waves which are transmitted from the transmitter. So those things we need to take care, and it is always better to perform this experiment in open place instead of like performing this experiment in a closed room, so which is not preferable. So it's always better to perform this experiment in an open space where you have less reflection from the wall or surrounding. Okay, so those are the things which you need to take care. And here is how the observations you can take. Simply, you can start from zero point 0.5 centimeter or 1 centimeter at the interval of this, and you can measure the power, and you can take few set of observations. Then you can plot the graph. You will receive something like this. So you can fit it with some fitting application and software. Okay, so what we expect at the end of this experiment, the graph something like this. Okay, so we'll come to the software side. So there are different software for different OS. Okay, for example, Wireshark works on all the three platforms. but it has some issues. Like it also works on Mac OS, Windows, and Linux, and we need to see. But it works majorly very good for Mac OS as compared to Windows and Linux. So we recommend Wireshark for Mac OS, but they're also available for Windows and Linux. And Wisdom Blur is best for Windows, and it doesn't have it's not available for Mac as well as Linux. And Prakash has written a Python script for Linux, so we have already shared with you so on both Moodle and Slack platform so about the script. And if you have any doubts, so we can discuss it. And for smartphone or Android platform, you can use Wi-Fi analyzer. So we have given all the links in those write-ups, okay, as well as uh, in the link which we have shared yesterday night or today. So you can refer that. And if you have any problem, so uh, we can take those questions in our next sessions. Or if you want, I can explain now. So just a second. So I will see whether I can show you. Yeah. Is my screen visible,
Yeah. Yes.
Prakash? Yeah. Yeah, we generally have three platforms here. Like generally, people use Windows. Like I guess most of you people use the Windows OS, and this Vistambler is for Windows OS. So you can download the Vistambler software from this website. This is already shared with you, so you can refer that. Okay. So once you install this, so you can go here, scan APS, where it will scan all the available Wi-Fi connection near to you. Okay, so for example, we have like scanned all the Wi-Fi connections near to us. Here you can see. Okay, and among this, we need to connect to one connections or one Wi-Fi router. For example, we need to connect here for Ashish device. Okay, so once you need to find that. Once you find that, when we have to make an filter. So you can go in the view section and you can go to the filter and add or remove. You need to add and filter here. So once you start adding filter, so this is the pop-up how like after kind of like uh, clicking on the add filter. So you can click here on a add filter. So once you start clicking, so you need to see and you can copy the MAC ID which is here and you can paste here and you can name it to filter one or your name or anything. So it's up to you. You can name the filter. Okay. So once you done that, so the filter one is already like prepared. So you have created already one filter. So after that, so you can go and connect to the filter one. Okay. So once you are connected to the filter one, so you can see the graph. So this is actually power with respect to the time. So the receiving power from that device or that connections, okay, you can see here. This is how it looked like. Okay, and you can see you can move little closer, you can take away, you should see the change in the power strength here. So this is how the software like should work, and this is the procedure how you need to install and like take the observations on this. Okay, and if you want to export it, and simply you can go on a file, export it in CSV format or any format, but we recommend you CSV format. And you can filter AP. So we need to take only observations from the filtered AP. Okay, so once you do that, you can see the active here. So it is taking from Ashish device. Okay, and it will take only those reading, and it will save at your desired location. You can give the path where you want to save. Once you save it, so you can later plot it. So how to plot? So once you get in the CSV format, so RSSI is actually your signal strength, and this is the uh, slot or time stamp. So you can plot these two things. So once you select this, and you can plot graphs in something like this. So you should be able to see the output here, and you can see the variation in the power with respect to time. And when you move closer or away, you should be able to see something like this. This is about wisdom law. Okay, so the manuals are given to you, and you can refer this. And if you if you're facing any problem, so we are available on the Moodle platform as well as on the Slack platform. So you can ask us. And similarly, for Mac OS, Wireshark is here. So one, you can download the Wireshark from the website, wireshark.organization or the org. Okay, and once you start, you should be able to see. Uh, yeah, we'll take few questions like once I finish this explanation. So I see some answer rising here. So yeah, you should be able to see something like this, which means we are receiving the power from the Wi-Fi, and we need to select here the wireless if you are using Wi-Fi. So anyway, we are using Wi-Fi here, so we can connect to wireless. Once it is done, then you can go to this icon and start it. Okay, so once you start, so you should be able to see the window something like this, and here you can see the trafficking. Here, one thing we need to take care. So untick this Promix, and you should be click on the monitor, then only it will work. And before that, you have to make sure export is installed in your like Mac, Mac devices. So if you're not, if you haven't installed the export, then it won't work. Okay, so we need to take care of that. And rest instructions are similar what we have mentioned like in the wisdom blur. Again, we have to make a filter here. Okay, so the instructions are again given here clearly. Then you can follow this, and after applying filter, so here like you can see apply filter and click on the selection. Okay, so once you applied the filter, and you can go to input output graph. Once you click on it, and you should be able to see the graph something like this. So this is simple, and once you like start getting graph similarly what we have shown here on the screen, and you can save somewhere else in desired location, and you can plot it later also. So this is simple about this. And the third software, which is the Wi-Fi analyzer, you need to take observation, and you need to note down somewhere, either on Excel sheet or somewhere else. Those are not directly recordable on any device. Okay, so I guess someone is asking question here. So I can see one. Yeah, Bhagwan, uh, you can unmute yourself and ask your question. Desh, anything else which I didn't mention here?
No, I think it's fine. Let's see what the questions are. That might
Okay.
prompt.
Bhagwan Kadali. So you can unmute yourself and you can ask your question. Okay, one question is here from Muhammad Rian. So why power oscillating as the distance changes? Yeah, of course. So once it is going away, so definitely the power will be less.
Now, is your question about the reflector? Why does the power change when the reflector distance is changed?
That will be depend on the distance between the antenna and the reflector. The one thing that is one of the reason. So if the distance is like uh, exactly where it's forming a constructive interference, you should be able to see the more power. If it's a destructive interference, then you should be able to see less power. So that is one thing.
Does that answer your question?
Yeah, you can add Desh.
No. I mean, I'm asking the person. Is that
Yeah.
a sense of the
Mohammad
question?
Rihan, yeah. So you can unmute yourself. Is that if you're not able to unmute, so you can directly type yes or no on the chart. Sanjana Patil. So do you have any question? Yeah, Mohammad Rihan said okay. So I guess he's okay with the answer. Desh, you want to add if I miss something?
I think the essential part is that there is a transmitter. The transmitter is radiating in its normal way all around based on its directivity. And if you put a reflector behind, the the signal falling on it gets reflected promptly, and the reflected signal and the already forward going signal interfere and decide the resultant intensity that an observer along the line of sight perpendicular to the reflector would see. And that uh, is subject to what kind of interference you get between the direct ray and the reflected ray. And what we are expected to see is when we get the maximum, it should correspond to the constructive interference, and that will be certain distance of the reflector from the antenna, and that you can work out, and you will find that that should be lambda by 4, where each way travel is lambda by 4. So the two-way travel corresponds to lambda by 2, which corresponds to a phase difference of pi. And on reflection, you get an additional pi. And these two to put together makes a phase difference of 2 pi, which makes it in phase combination of the reflected wave with the direct wave. And that's why we get a maximum there. You can work out correspondingly when the minimum would come. And you will find that there will be a specific relation between the when you get maxima and minima and what is the distance of the reflector in units of the wavelength. So based on whether you're using 2.4 gigahertz or 5 gigahertz, you will see different results.
Thanks, Desh.
That makes
So,
it clear. Yeah.
yeah. So there is a question. So how it is applicable in astronomy? Desh, can you comment on it?
Oh, yeah. No. I started speaking without realizing that I was mute. I had muted myself.
Okay. So how this method is used in astronomy?
Yeah.
So are the
So
use
there
of
are a
back
variety of
reflectors.
ways. It's essentially got to do with the directivity and the directions in which you do not want to look. For example, when we are looking up in the sky, we wouldn't like to have light coming from below, right? Interfering with our measurement. And one easy way of doing that is to have your antenna put a reflector which is parallel to the ground if you want to look up, and you will find that it cuts down the response from behind largely. It depends on the shape of the reflector, the size of the reflector, and so on. But largely, this is the basic principle. In the ray optics description, this becomes obvious. But what really is at work is the physical optics. So you need to really take into consideration the full wavefront and what is happening to it while working out the precise nature of the modification that will occur with the reflector. But in principle, you can see that when you put a reflector below an antenna in the radio astronomy context, you will find its upward response will be enhanced if we have put the reflector at the correct location below the antenna element. And what is that distance? It's typically lambda by 4. There could be other versions of it also, which will be different from this value by odd multiples of lambda by 2, or even just multiples of lambda by 2. And you will find that the larger distances will not be very useful because you will have less power reaching the reflector and so on. So the best optimum thing is lambda by 4. So what you will see is your gain in the forward or upward direction, in this case, is enhanced by a factor of 2 at the expense of power going in the other directions which you have blocked. And so this is how it's used in radio astronomy. If this antenna element were to be at the focus of a parabolic or paraboloid reflector, then you would find behind this element, which will appear as if it's at the top, but because this element is looking down on the dish surface, you will find a reflector. So those are the simplest ways this can be used. These reflectors themselves can be shaped appropriately if required, if it corresponds to better performance based on the reflectors or other primary reflector surfaces and so on, when it's used along with some other shaped surfaces. Does that answer your question largely? So this is used routinely to not receive any radiation from the ground, because when you make sensitive observations, you want to look at the sky. You also want to block the light coming or signal coming from the ground. So it serves both the purposes: blocking things coming from behind, in this particular case from the ground when you want to look up, as well as enhancing the response in the upward direction, which is more desirable.
Thanks, Desh. So there's question from Shlok Shah. So he want to know the use of filters. So actually, like around you, there are a lot of Wi-Fi signals, right? And you are interested in only one device, Wi-Fi signal, which is coming from a specific device, and you have to plot the power which is coming from that device. So that's why you need a filter. You need to filter out, okay, other, and you want to connect to only one device. So that's why we need a filter to like extract the like one power among so what you're receiving. So I guess
it is just to
that's
select which, much the way you put a filter when you select one of the Wi-Fi connections that is available, right?
yeah.
You actually put a filter implicitly. Here, it's in the context of which power you want to display and measure. Instead of, you can also have without filter, but then you would have search yourself for the power associated with the connection of interest.
Okay, so how to plot like the saved form, because there are many people who are asking so how to plot using different scripts like Python or using MATLAB. So there are like similar questions here. So you can save like whichever form like software you're using on whichever platform. So you can save those files in CSV format, and those are readable, okay, in like any tools, whether using Python, MATLAB, Origin, or anything. So those are easily readable, and using those data, you can plot it. So these are simply plotting softwares you're using, and you can also fit the best fit curve and other things. This is simple, very simple. And if we take different shape, so does it work in a similar way? Of course, if you take any metal shape, whether it's aluminum, copper, iron, or anything, so they work in a similar way. It will not affect to the output. Okay. So
Yeah, if the
the only,
query is related to the smoothness of the reflector,
yeah,
because you must have noticed in the picture that Jameer showed, the aluminium foil seemed to have some, it was not as plain
smooth
as
as the copper one.
the copper one. The rule of thumb, which can work out also formally, is that wavelength divided by 20, those kind of errors in the surface accuracy are not important. Or once you have, so here you can do a quick calculation. If your wavelength is even take the shortest wavelength in the two cases that we mentioned about the frequency of the Wi-Fi, which is what 5 gigahertz, which means 6 centimeter. 20th of that will be about third of a centimeter. So any ondulations of that order in the surface will not matter significantly. It's not that they don't matter at all; they do matter, but the errors resulting from that are negligibly affecting the outcome.
Thanks, Desh. So there's a question from Akshat. As we have seen that the receiver is receiving a constructive interference at the other end, does it also mean that the overall strength coming the transmitter has also increased?
No, it's comes at the expense of what is not given in other directions. Okay, the transmitter does not know really that you have put a reflector there, so it's continuing to transmit the power at the rate that it does. You are directing it in a certain direction more and certain direction less. The total power radiated integrated over 4 pi steradian is conserved, if that answers the question.
There's another question. So, will the absorption of electromagnetic wave in the metal shape affect the experiment? And what would happen if any surface is reflecting and refracting also?
Well, there is, if you look at the detail level, you will find the electromagnetic wave actually propagates through the metal up to a certain depth. It's called the skin depth. And uh, the, the propagation is attenuated exponentially as you go to the higher depth within the metal. And so there is, if you like, certain reflection, right? Or some finite thickness of the metal participating in this. But you could have other situations where some other kind of material is there, and based on its reflectivity, because what matters is what is coming in the forward direction ultimately, which would interfere with the direct signal that was reaching us anyway. So you could have any complex situation. It could have even multiple reflections and come in the direction of interest. And then we ask a fair question as to what these combinations of signals coming from various regions, no matter how they have been treated, finally have what phase relationship with the forward rate. And the sum total of vector sum total of that is what we will see as the deciding the net intensity in that direction.
Thanks, Desh. So the next question is from Anudeep. Is large dish like Arecibo better than number of dishes spread out over a large area like SCA or UHD?
It depends on what the aim of the in terms of use of the telescope is. Certain purposes will prefer, certain studies will prefer um, small dishes spread over larger area like SKA, which will give you wider field of view, wider region that you can look at any given time, and fine angular resolution if you have spread them over large distances. But it will have dilute aperture. The sensitivity will be finally decided by the number of buckets you have times area of individual bucket. Whereas Arecibo, like telescope, will have narrow field of view based on the size that it has, based on the wavelength at which it is used, which is lambda upon the diameter of the telescope. And it will have better sensitivity for sources uh, which are fatter, whereas the SK like distribution or GMRT like distribution or VLA like distribution of small antennas spread over wider distances will have better angular resolution and poorer sensitivity for broad sources. Depends, of course, on what is the smallest separation between any pair of antenna that you would have at the best case. But it'll certainly have better sensitivity for compact sources. So point-like sources will show up better in these arrays, whereas they will you will not have adequate resolution with the Arecibo-like telescope. So those are the differences. There are many other differences, and if you really want to make a comparison, it should be based on what is the aim, what kind of sources you want to look at, and then you will find, based on that consideration, you will actually decide which telescope is better. So it's not one single answer in terms of this comparison.
Thanks, Desh. And the next question is, how would we determine the frequency emitted from the smartphone as a transmitter? So basically, when you start transmitting at the receiver side, you can see while applying the filter, whether it's operating at 2.4 gigahertz or 5.5 gigahertz. Okay, directly you can see if you go the properties of the filter or the properties of the receiving channel, and it will also tell you at what is the central frequency and what is the bandwidth. So those information can be like extracted from the from the softwares, okay, while applying this filter. So I guess hope this answer to your question. And the next question is, during the experiment, when we fix the reflector at a distance, will there be a fluctuation in the power reading? And if that happens, which value should be focused on? So yes, of course, there will be a fluctuation, a slight fluctuation. So you need to like wait for a few minutes or few seconds or minutes. Okay, still if you're getting the fluctuation, a slight fluctuation, say like in points, so maybe you can take the average. Okay, so that is the best way what I suggest. So is that right, Desh? So taking average is a good way.
Yes, there could be some inherent accuracy, the level of accuracy you might get from a measuring device, and the noise in the measurement will show up in terms of these fluctuations, even if nothing else is changing. And so, in such cases, improvement of the measurement value can occur easily by taking the average. Please remember that these are already log values when they are expressed in dBms as power. So while averaging, be careful. In linear scale, a value dropping by 30 dB is just dropping to closer to relative zero with respect to that value at the top. But largely, I think it will work well. to take average of values which are roughly in the range that you're already at. There's a question. I didn't realize that initially, but it looks like sent to only to me. So I will read that.
Yeah, sure. Yes.
It says, what is the model or equation to fit that plot? Is that any specific for all observations, or we have to predict the model by seeing the observation pattern to get the best fit results? I think the simplest model here is that there is a direct ray and there is a reflected ray, which has phase difference due to round trip that it does to the back reflector and additional pi phase shift coming from the reflection. So if you take distance d to the reflector, d divided by lambda times 2 pi times 2 for the round trip plus pi, when this total phase shift is integral multiples of 2 pi, you will get a maximum. When this is odd multiples of pi, you will get a null or minimum. And the variation in between, after all, what you have is something equivalent of 1 plus cos with some phase shift, right? And you can easily see that this can be expressed as cos square pattern, okay, with appropriate argument. So that's the model and that's the fit. Except as you move the reflector further and further from the from your radiating antenna, you will find that less and less power is reaching and less power is returning. So there will be an overall droop in the power that you would see with increasing distance. But other than that, it will be a more cos square like pattern. Okay, with the argument changing linearly with distance. Does it answer the question, Shubhadeep Datta? Yeah, there was some message from Sanjana. Did she have some question, or it was just a courtesy hello?
Yeah, she asked some question directly.
Oh, she did ask. Okay,
Yeah.
later. Fine.
So I have attended those questions. Prakash, you want to add anything?
No, nothing from my side.
Okay, so in next few days you can try this experiment at your home. Okay, so if you face anything, so you can directly write to us. So we are available on Slack as well as on the platform. Okay.
Yeah, and in addition, we will have this busy hour. Okay, which
During
is
that we can discuss.
carved out for actually doing the experiment as you do. We will be online and might be able to help you with questions that might come up when you actually try it out, even if you are not able to not have done it earlier.
But yeah, don't wait for that busy hour. Get started.
Right.
Ideally this weekend, just get the software installations done. If you have any problems, raise the issue on Slack or the Moodle forum, so that even if we do not immediately get back to you, one of your members who are participants can help you out if they know the solution.
Yeah, so in the past, we have noticed that so in the software updates, something may be changed. Okay, it's not exactly we have explained. It's not exactly how we have written the procedure. So you may find there might be some slight changes. Okay, that is due to some software updates. Okay, so that we need to take care.
Dibakar Datta, you can unmute yourself.
Can you just show what kind of when you were showing the slide about the observation and the example, can you just repeat the slide once again? So I'm not able to get it.
Can you speak louder? We
Yeah.
couldn't hear you
I also
properly.
could make out.
Hello. Yeah. Am I audible now? Hello.
Yes,
Yeah,
better.
yeah, it's better.
Yeah. So, sir, what I was telling you is that you have shown us the graph about the power versus resistance. So, how will it look like? I mean, can you just repeat the slide once again? Can you show us the slide again? I mean, that slide.
Okay, he wants to see that plot to ask the
Yes,
related question, I think.
yes. The slide you have shown in your presentation.
Yeah, so Jameer, if you could bring up the slide back again on the share.
Okay, just a minute. That is what I want. Which slide you want?
The plot.
Okay, so here's the sample plot. So what was the question? So I was not able to hear. Hello?
Are you able to see the plot, Mr. Datta?
So what was the question there?
I don't know. He wanted to see this plot. I think he's still online. I can see his name here. Whether he's able to hear us or are we having difficulty listening to him? It's not clear. He's certainly muted right now. Are you able to hear us, Dibakar Datta?
Just I can see the chat.
He's
cannot unmute the plot. He is not able to unmute himself.
Oh, I see. Okay, so he can. Okay, we should allow that to be unmuted, right? Ask to in. Okay. Yeah, you should be able to unmute yourself now. Hello. Is there something he's writing in the chat?
He said no unmute.
No, I enabled the unmute. Maybe one of the Santosh has to do that, or you try.
Yeah. Now it's okay. Now it's okay, sir. I've been trying to unmute myself. Sorry. Yeah. I have got my answer because I wanted to see whether that thing is software pattern or not. That's what I was. Yeah, sir. Thank you, sir. I was just unable to unmute myself for a long time. I was just.
That's okay. So for the benefit of others, what is the point that you wanted to see, or even share it with others?
Yeah, that is what this is the software pattern. That's what I wanted to see. It's a sample result. We have done the experiment. So the observation for the observational table, you have given one table that is for distance versus power.
So can you just show that table again? Yeah, fine. So this is how we need to write down the results and to plot it. Yeah, that is what I wanted to see.
Except while plotting, you might want to convert the power from the dBm scale to milliwatts in linear scale. Okay. And then plot. That's when it will be a proper cos square pattern. Okay. All right. Are there any other questions or comments?
See any question here right now, and if you people want to share anything or have any questions, you can raise your hand or you can send
Yeah,
a
you
message.
raise your hand and then we can unmute you. Okay, looks like there isn't.
If there are no questions,
unless there is something on the chat.
No, I don't see any message
in
the chat box. So if there are no questions, we can end the session. So we'll meet next week.
Okay, so thank you everyone. And we will stop here. As Jameer and Prakash mentioned to you, please go ahead with the experiment and installing the appropriate software. And if you face any difficulties, you can post it on the Slack, and there could be help coming even from your peers, including us. All right, then.
Thanks.
Okay, thanks, Jameer.
Thanks, Desh, and thanks, Prakash.
Thanks, Santosh.
Thanks.